My name is Charles Miller. I was supposed to be here to talk about Leopard, but for reasons that I'll talk about in just a second, instead, I'm going to talk about the iPhone. So if you're here and you're dying to learn about Leopard, please read the conference paper I submitted. It's got everything I wanted to say, but I'll explain just shortly why I switched topics. So the talk today, brief introduction. My old talk, which was originally supposed to be an hour long, but then it was going to be a 20-minute turbo talk, and now it's exactly 4 slides. Then I'm going to talk about Mac security in general and why it's not so good and why breaking into these things is relatively easy. And then finally, I'll talk about the iPhone exploit that myself and 2 other guys in my work put together and how it works and what we had to do to get it to work. All right, so what happened to Leopard? Well, one thing that happened was it got delayed. So it was supposed to come out when I submitted the talk. It was supposed to come out in May or June. They pushed it back because of the iPhone. So it really would have limited what I could say anyway because I've only seen it under NDA. Everyone wants me to talk about iPhone anyway. So and like I said, everything that I was going to say about Leopard is in the conference paper anyway. So just take a look at that. Okay, so what about Apple and security? Everyone, the prevailing belief is that Apple is more secure than Windows. I don't know if that's true or not, but their website certainly thinks so. So they say Mac OS X delivers the highest level of security through adoption of industry standards, open software development, and wise architectural decisions. And then they say that Apple engineers designed Safari to be secure from day one. So they're very sure of themselves. So why take the time to even try this? Well, so far they're still pretty small in the market, 6.5%, but they're growing. All the cool kids are doing it. So they had the month of Apple bugs. So they released a lot of bugs in Apple's there. They had the Hack a Mac contest where someone found a QuickTime bug and won a quick 10,000. And then Safari, which was so highly touted on the previous slide. When they released it for Windows, researchers found 18 vulnerabilities on the first day. Plus, it's always fun to just shut up the local Mac enthusiast. Okay, so this is the part of my old talk that I just couldn't live without telling you guys about. So one of the things about Macs, as opposed to if you came from a Linux background and you expect ptrace to actually work, it doesn't. So on a Mac, you can't read or write registers or memory using ptrace. You have to use what's called the Mock API. And to help myself do research and hopefully others, I ported PyDebug to Mac OS X. It's not 100% done, but it's usable. And PyDebug is a pure Python debugging API, which is it's natively it was designed to work on Win32. And the reason I did that is it allows the use of the PyMay framework, which is a very powerful reverse engineering framework that I'll recommend you use. So you can download this port that I wrote from the site, the PyMay site. And you can't really see it, but this is a screenshot of the file fuzzer module running for PyMay on a Mac. All right, what else did I want to say about Leopard? It's going to have dtrace, which is going to be really cool for vulnerability research. So dtrace is a dynamic tracing mechanism. It's built right into the kernel, so Apple had to do a lot of work to get this working in their kernel. It uses the D programming language, which is a subset of C, more or less. Basically, there's all these probes located throughout the entire kernel, and they can be accessed through things called traces. And what's cool about it is that when the probes aren't active, they don't slow down the system in any noticeable way. So basically, they're always available to you, and they're designed basically. This dtrace is designed basically for system administrators to be able to do debugging activities on production servers. And check out the manual. But what I see it for is a great opportunity for researchers and vulnerability analysts to write really great tools really easily. So, and I have examples of all of these in the conference paper. So you can write a file system monitor like FileMon and NetMon and basically like 2 or 3 lines of this D programming language. You can rewrite ShareFuzz, which is a environment variable fuzzer, in a couple lines. You can write ltrace, strace, whatever you want. And again, I have examples of this in the conference paper. You can get instruction traces, so you can figure out exactly which test cases you're testing, go down which code paths. You get code coverage for free, so unlike PyMate, which requires you to use IDA Pro and use debuggers, this you'll get basically the p-stalking functionality, and it won't even slow down because you don't have to worry about the breakpointing and the slowdown. So, and lots more. Check out the paper. Okay. So I made a claim earlier that Macs are easy to hack into, and now I'm going to try to convince you that's true. And the fundamental reason that they're easy to attack is that they're easy to use. So, Apple's big deal is that Macs, they're very easy and friendly, and they really are. And to enable them to be friendly, they have like an absurd number of set your day root programs. So there's at least 50, and a large number of them you'll never have heard of. So those are very suspect that there's basically no documentation on them. They're there, they run, and they seem to take something on standard in or out. But I think with a little research, you could probably manage to elevate your privileges with that. And then there's a few old ones that are around that those haven't been set your day root on a Linux box in like 2 years, and they still are happily on a Mac. Safari is the default web browser for Macs, and it's very friendly. It's very easy to use, and that's what's the problem. So it has a huge attack surface. So all these programs I listed on here, Safari will spawn those for you if you try to browse to a particular file type that it corresponds to. So if you browse to a page and you click on an MP3, it'll launch iTunes, for example. And so the point is, not only do you have Safari to look for bugs in, but you can look for bugs in all these other programs too. And if you find a bug in, say, iTunes or Help Viewer, there's been one. So you find a bug in one of these obscure programs, it turns out to be the same as a client-side Safari exploit. So you got a lot of places you can look for bugs if you want to try to get someone with the client side. A great little tool that it has is called Crash Reporter, and it monitors all your programs. So if you're into fuzzing, like I am, one of the first things you have to do is monitor the target that you're fuzzing to make sure that you know when it crashes or when there's been a problem. And you don't have to do that on a Mac. It does it for you. So you can just fuzz away. You don't have to worry about it. And Crash Reporter will monitor all your programs, and if anything crashes, it records it to the system log, and also records a crash dump for you. So very convenient if helps you fuzz. For some of the stuff, like WebKit, there's some source code available. So source code makes your life a little bit easier because you can compile it however you want with symbols, or you can instrument it to give you code coverage. More information in your crash reports. Exploitation is pretty darn easy on a Mac. So they don't randomize anything, unlike most operating systems. So they don't randomize where the stack is, where the heap is, where they load libraries, where their binary image is loaded. On top of that, the heap's executable. So you start your shellcode somewhere, jump to it, and you're in good shape. And everyone hates to upgrade or update their systems, and luckily Macs don't make you do it so much. So here's a chart, and it shows some versions of some open source software that are on Macs, and then the corresponding version that's on available through open source. And HD sort of stole my thunder a little bit on the final bullet in his talk, but until earlier this week when a patch went out, they hadn't upgraded Samba in like 2.5 years, and there was at least a few pre-auth remote root exploits that you could have against Macs, and there was some actually in Metasploit that you could just point and click, and as long as they had file sharing on, you could own it. Okay, so that was why Macs probably aren't the most secure platform, and some of that will play into why we were able to actually get the exploit working on the iPhone, because the iPhone basically runs a stripped-down version of Mac OS. Okay, so here's my formula for if you want to find a 0-day on a Mac. This is what you do. So you find an open source package that they use that's out of date, and like I said in the previous slide, there's plenty of those. You read through the changelog for that software. You find a bug that's been in a newer version, and you're done. So this is a way that you can find a bunch of 0 days on Macs using like VI or More or grep or whatever your favorite tool is. So you don't have to worry about static analysis or fuzzing or any of that stuff. It's too hard, so you can just do it with a text editor. So what are some examples? Well, WebKit uses it uses part of this Perl regular expression PCRE library. It doesn't actually have the version number anywhere, but just by looking at it, it looks like it's around version 6.2. The current version is 7.2. And if you look, a year ago there was a bug reported, and it was fixed in version 6.7 of PCRE that says a valid though odd pattern that looked like a POSIX character class, but has an invalid character after the bracket, causes a internal error code overflow message. In some cases, causes a crash with the glibc free error. Well, that sounds like it could possibly have security implications to me. This is the actual JavaScript that if you surf to a page with that JavaScript with Safari on any platform, it'll crash. And it turns out that it's a heap overflow. Every time you put a couple of those little brackets, something, something, and another couple of brackets, you basically overwrite 2 bytes in a heap buffer. Because of the limitations on how big that regular expression can be, you're limited to writing 4,000 bytes past the end of the buffer, which is quite a bit. Since it's in WebKit, it's in all the applications that use WebKit, including Safari, Mail, and so forth. And it's vulnerable in Safari 2 and then their new 3 beta version for Mac desktop servers, iPhone, and Windows as well. Is it exploitable? Yeah, this is actually the bug that we use to take over the iPhone. And I should say, in the interest of full disclosure, I didn't find this one by using the text file changelog technique. I actually found it with fuzzing. But this one I did find with the changelog technique. So when you're a Mac researcher, it's another changelog entry, another Safari 0 day. So here's one. It says, it talks about subroutine references being quantified, and then it gives you the same sort of error condition. So if you get internal error code overflow, or there's a glibc double free corruption, that's probably pretty bad. And again, this was fixed in PCRE 6.7, which came out last year, but Apple never bothered to actually fix it in their source code. And here is more JavaScript that if you go to that page in an unpatched browser or iPhone or whatever, it'll crash. And I should mention that these bugs were fixed earlier this week by Apple, I think on Tuesday. The only thing you need to pay attention to is the iPhone, by default, when you sync it only checks once a week to upgrade itself or update itself. And it's just sort of random, like what day of the week yours happens to check on. So, so you have like a 3 in 7 chance if you haven't pressed the force and update button yet to get upgraded. But so please do that. Okay, so that's the vulnerability. Now I'm going to talk about how we actually got the exploit to work. So the problem with the iPhone, from our perspective, was that there was no way to like get on this. It's not like a real computer where you can't like SSH in and do stuff. So you couldn't get on it. You couldn't run a debugger on the process to see what was going on. It was really sort of black box. The only thing you had going for you was Crash Reporter. So the iPhone had, just like a Mac OS X, desktop or whatever, it has Crash Reporter, and it'll give you crash dumps and logs, and it's sort of useful. So what we did, and we knew that these 2 bracket, star, bracket, if you throw one of those in, you're going to get 2 byte overflow. So what we did was we wrote a fuzzer, and its purpose wasn't to find a bug, it was to take control of the system. So we would randomly throw in a bunch of these little primitives that would overflow the buffer, and a lot of like long strings and other stuff. And we just fuzz the heck out of the iPhone. And then every so often we'd sync it up, download, a couple hundred crash reports, and we would just look through them and we hoped for the best. And eventually we found one that looked promising. Took a couple days. So this is, if you have an iPhone, this is the little screen that it says when you sync. It's like, oh, I've noticed there's a problem. Do you want to send this to Apple? And I said, no. Until a couple days later, and then I finally said yeah. But during the research phase, I made sure to say no. Okay, so here's the crash report. And the crash report only gives you the registers. It doesn't give you any of the memory information. So it still isn't everything you would really want, but it's promising. So the things to look for in this crash report is that the registers are R3, and this is ARM architecture, by the way, which is another sort of complication. So R3 and what they call IP, what I would call R12, they don't look like totally random, so it's possibly that was something we sent in. And if you look at the program counter, I have it disassembled there, and you can look at the highlight, and basically those two registers, R3 and R12, is performing like some sort of unlinking of a linked list or something. And since this crash actually occurs in libsystem.b.dilib, that's the max version of libc, basically. So you're unlinking a list in libc, it's probably just some kind of old-fashioned heap overflow. And all that really matters at this point is, can we really control R3 and R12? And the interesting thing about it is the way that they do memory allocation on the desktops, for example, doesn't use a linked list structure. So I'm not sure exactly if they did it just totally different on the iPhone or what, but the best thing is you don't really have to know how it works, you just have to know it works. Okay, so it turns out that with a little looking, we saw that R3 and R12 come from what's called a compiled regular expression. So you pass in a regular expression, and the PCRE library does something to it and stores it in an internal format, a compiled way. And those values that were in R3 and R12 are exactly things that were in this compiled regular expression. So then all you have to do is figure out, well, is there a way that I can make anything I want show up in the compiled version? And the answer is yes. By using character classes, you can do that. And so then a couple crash reports later, I found this one where I was showing off the fact that I could control R3 and R12. So and it still crashed at the same spot. So at this point, I'm going to be able to do the unlinking with 2 pointers that I control, which means that I'm going to be able to write 4 bytes anywhere I want. This is the corresponding HTML page that gave me the little Babe Cafe dead beef thing, if you want to try it for yourself. Okay, so I can write 4 bytes anywhere I want. I still don't have a debugger, so the question is, what do I overwrite? So what we chose to do was basically just, we knew where the stack pointer was, so we just started heading down the stack and figured there's going to probably be a saved return address somewhere, and when we overwrite that, then we get control. And then for the other value, we also chose a stack value because of the way that the unlinking works. You have to make sure it's writable. So we were sure that the stack would be writable. So we basically just sent in 2 stack values for those 2 pointers, and we changed one to, we kept incrementing it by 4. And eventually, sure enough, we got a crash report back that said that the program counter, when it crashed, was on the stack. So we had control at that point. And if you look at it, so it was on the stack, it crashed, and it crashed with a bad instruction, which makes sense. And like I say here, so not only did we get control, but we also learned that the stack is executable on the iPhones. And that's true on the old PowerPC ones too, but not on the x86 Macs. Okay, so we now controlled the program counter, which in x86 parlance would be EIP. And the question is, all we got to do is put some shellcode in there and jump to it, and we're in business. Turns out it was the hardest part of the whole project probably was finding our code in memory. So sort of counterintuitive, and if you want to find out why, I'll tell you offline. So the way we finally figured out how to do it the right way, we basically just tried brute forcing it and it didn't work, was we ended up figuring out a way to get the iPhone to give us core files. And the way we did that was we used these tools that the iPhone dev hacking group or whatever they want to call themselves, that they're this group that's interested in unlocking the iPhone. They wrote some cool tools that we used, one of which was Jailbreak, which lets you have access to all the files in the system. Then we went in, and just like on a regular Mac, we configured launchd.conf file, and sure enough, it started dumping core files for us in /cores. So what we would do then is after it would crash, we'd go in, we download the core files, we check them out, and it turns out regular GDB doesn't really understand the core file too much because it's expecting an x86 file, but it turns out it can read the virtual memory, which was all we cared about. So we were able to find where our code was in memory. And you say, well, you found it once, but what about the next time? Well, luckily, again, Mac doesn't do any randomization, so it's always in the same spot. It's very, very kind of them. It was friendly. I love my Mac. So then we had the program counter. We knew where to put it. We just had to have it do something interesting. So this is actually the second set of shellcode we wrote, but this is the one that we sort of demoed to people, and it was the privacy stealing shellcode. So what it did was pretty typical stuff. It called socket, connected out back to our web server, opened up particular files containing stuff like your text messages or whatever, and then just wrote them across the socket. So we wrote it in assembly, and then we used on Linux x86 to ARM cross compiler. And the only thing that was even tricky at that point was just to make sure that the syscall numbers were the same. And so we did a little reverse engineering of some of the iPhone libraries and binaries, and it is. So it's exactly the same as on a Mac, the syscall numbers. All right, so that was one thing, but how many times in your life do you get to write, take over something that's not just a boring computer, it's like a device. So it's like, well, let's write some shellcode that does something slightly more interesting. And the way you do that is just start tearing apart some of the libraries that are on the iPhone itself. And so these are, and they export all their functions in the libraries by very descriptive names, which is great. So these are some of the ones that I saw that I thought looked pretty interesting. So audio services play system sound, and that's from a library called Audio Toolbox. CT call dial, CT send to voicemail, and that's from the Core Telephony library. And SMS message create and SMS message send. So all you got to do at that point, you're running as root. You just got to figure out, how these functions work and how they're called, and you can call them. You can do whatever you want. So it turns out that it's sort of complicated. So we chose the easiest one, which was the play system sound. I'm not sure if you can read that, but at the top is the IDAPRO version of that function, audio services play system sound. IDAPRO has told me what address to expect that at, and since there's no randomization, that's exactly where it is every time. And then on the left is an example from the mobile phone application of them actually calling that function legitimately. So all we did was look and see how it's called by them, and we just do the same exact thing. So this is the assembly language that we wrote, that we compiled using the cross compiler, stole the bytes out of it, uses it as shellcode. And it works. So what that shellcode did was it makes it just like when you get an email if you have an iPhone. So it goes like ding, and then it vibrates. So it was sort of fun. Like, you go to a website, and then your phone, Safari sort of disappears, and your phone starts vibrating. So it's kind of cool. But anyway, this slide is just about, Macs have security problems, but I still like them. So I'm still friends with my Mac. So questions? The iPhone slides up anywhere? What's that? Oh, I'll put these up on our website, so it'll be on that Exploding iPhone website. See, I still have my iPhone too. I haven't tried it.
It should have been on our website.
It says it works. The one interesting thing from our perspective of jailbreak was that once you jailbreak, at least the jailbreak we had back then, like now there's a debugger and everything, so if you wanted to redo this, it'd be real easy. But when we were doing it, there wasn't a debugger. But what jailbreak did for us that was bad was once you jailbreaked, you couldn't sync anymore. And since we couldn't sync, we couldn't get the crash reports. So what we had to do, which was easy in retrospect, was you could jailbreak so you could get the core files, which is what we needed for it. But also it stores the crash reports there too. So all we did was while we were getting the core files, we would also download the crash reports as text files, and then we didn't have to sync. But yeah, so those guys really helped us out, unknowingly, I guess. But so we used a lot of their tools, and we also used someone wrote a little modified IDAPRO configuration file or something that allowed us to use IDAPRO for these files too. Yep.
So Apple obviously released the update the day before Black Hat. So had you been in touch with them for a few weeks before, or were they pretty quick? I mean, obviously they didn't sit on it too long, right?
So I gave it to them a couple days before anybody. So they've known about it for about 2.5 weeks. And in the initial email, I gave them basically this talk. So all the technical details. I gave them a patch for the actual, so it was easy for me to make a patch, and it makes me sound like I'm real smart or something, but all I did was do a diff between PCRE 6.6 and 6.7, and I sent it to them. So they had the patch in source code, and then I told them on August 2nd I'm giving a talk, and I'm going to release the details, so have the patch ready. And it was then their part, it was basically they could either do it by then or not, and it was, they decided to do it by then, and I'm glad. But yeah, they didn't really contact me, but yeah, they did it. Other questions? Okay, well, thanks.